While R squared is a good measure of the predictive power of a model, it's not the only criteria you should use for choosing a model. Model choice should be based on contextual understanding of the phenomena and the usefulness of the model as well. So, in this example, we're talking about fishing line. So, fishing line is sold according to its breaking strength. Since stronger fishing line is thicker, less line can be put on a spool. The table shows similarly priced spools available at an online fishing shop. What is the relationship between the strength of the fishing line and the amount of the spool? So the first thing we can do is we can generate a scatter diagram on the graphing calculator to determine which models might fit. So here's our original data in this table on the right, the strength and the length. And so our strength is our x value and our length is our y value. So our strength is our independent variable, our length is the dependent variable. So we're saying that the length that fits on a spool depends on the strength. So looking at this, it appears if an maybe exponential, maybe a power model might work well. So we're looking at it and it generally tends to curve downward. So we're saying, okay, either power or exponential models fit that shape, so we should start there. So in this context, since we are dealing with length and volume, a thicker line is stronger, a power model is a likely candidate. So choose an appropriate model, not just by the shape of the data, but also by the nature of the phenomena that we are modeling. So we're going to find the exponential model and note the coefficient of determination. So finding the exponential model, we get L is equal to 1060 times 96 hundredths raised to the x, where R squared is equal to 0.779, so 779 thousandths. And that's our exponential model because we have a number being raised to the exponent. Okay. So although this model is quite strong, we should not choose a model based solely on the value of R squared. We must also consider the overall fit of the model, the context of the data, and the usefulness of the model. While this model works well for many of the data points, it seems to be severely under-predicting the lengths for low-strength values. So if we look, this part of the graph does not look like our model is in a good relationship with those. Down here, as the strength gets larger, the points fit the model, but in the beginning, not so well. So we'll do the same thing with the power model. So for the power model, now we have the length is 4050 times s raised to the negative 0.801. So this is a power model because our variable is being raised to the exponent. And this time we have a coefficient of determination of 0.891. Not only has the R squared value increased, but the power model appears to follow the trends of the points much more closely. So you can see that these points over here, where the exponential model did not fit them well, now it works really nicely. And it still works nicely for the points on the right-hand side. So, which is the better model? The power model does indeed appear to be a better choice for this data. So when you're choosing a model, don't just choose the better R squared value, also talk about the trend of the points and how the model fits it as compared to other models.